Hi everybody, I'd firstly like to say welcome to Source Talks on Scala. For those attendees who are not familiar with Source Group and our brands, we are international recruitment specialists specialising in tech and life science recruitment. At SGI, we're on a mission to achieve the highest level of customer service, driving sustainable improvement and investing in our people. Source Talks community is a global community bringing together experts and leading professionals to discuss the challenges and changes they face across their organizations. Through our meetups and media series, we're pulling back the curtain to talent and technology and building a powerful community of people on the same journey, looking to achieve similar objectives. Without further ado, I'd like to welcome my colleague Francis to intro our talk today.
Thanks very much, Imogen. So, for those who've been here before, I'm sure you remember me, but my name is Francis. I'm here to welcome you to our series in Source Talks on Scala. So as Imogen mentioned, we are inviting leaders within the community to showcase how they're leveraging Scala and the ecosystem to build great digital projects and products even, and solve real world problems that I'm sure many of you will be encountering in your daily lives. I'd like to introduce our two guest speakers today, Kai and Pavel Shirshov, who are independent Scala consultants and functional programming enthusiasts. With many years of hands-on commercial programming experience, their contributions to the open source community include things like izumi-reflect, Distage, and many others besides. So just a little bit of housekeeping before we kick off. The talk will be 45 to 60 minutes. We're going to have a talk and then a live coding demonstration. And then after that, please save your questions because we'll have a proper Q&A at the end so it doesn't get messy. But please feel free to post any questions you have in the chat and then I'll facilitate that once everything is finished. But I will, without any further ado, hand over to Kai and Pavel.
Thank you, Francis. So, hi everyone. Thank you for coming. This will be a talk about application design and our approach to make it easier and more enjoyable. Once we finish with the slides, there will be a short but impressive demo. And if any questions arise during the talk, please post them into the chat or ask them then. We'll try to answer all the questions you may have. So first of all, let us introduce ourselves. Our names are Pavel and Kai, and we are from Septimal Mind, an Irish software development consultancy. We focus on productivity of engineers and team efficiency, and we are big fans of Scala and purely functional programming. Also, we participate and contribute to a variety of open source Scala projects. So, today we are going to discuss one question, which should be important for all of us. How do we manage complexity in real-world projects, especially in big enterprise projects? And we know that complexity grows naturally. It limits productivity and may bring projects and even businesses to a halt. And there are, of course, multiple answers to this question. But the essence can be expressed with just two ideas: shift the problems left in the development pipeline and use modular design and apply modularity everywhere. The shift left approach means that you should try to detect potential problems as early in the development pipeline as possible. Advanced languages with sophisticated typers follow this approach. Automating testing follows this approach. Acceptance testing follows this approach. Automatic acceptance testing follows this approach too. And of course, functional programming itself follows this approach. And yes, formal proofs, they definitely do follow this approach. And that's the best thing we may achieve to have a formal proof. So, and modules in their turn are independent and reusable building blocks, artificial boundaries, which limit the interaction between various parts of a system and reduce the overall complexity. And Scala gives us unmatched opportunities to use modules in functional programming environment. And for the best approach possible, we should combine together dependency injection and the tagless final style. And when I say dependency injection, I mean something a lot more powerful than Spring or Juice. So let's have a look. What actually is dependency injection? The answer is simple. It's a magic mechanism which performs wiring automatically. So it takes various parts of your application and combines them together into a working application. And of course, there are many different approaches to wiring. Like we may do it manually, or there are multiple ways to do it semi-manually. Though wiring is not an easy problem at all. There are up to at least 20 various aspects which may or should be handled during application startup phase. And manual wiring is extremely inefficient because you have to handle even the most basic aspects like operation ordering manually. And this task, it has worse than linear complexity, and humans aren't good at all with such tasks. Moreover, manual parameter passing, that's when we call constructors explicitly, it's just a pure evil, because often it forces us to change many locations all around our code base, even after a minor change or a minor refactoring. And the worst case scenario for manual wiring is configuration support. We may want to have some configuration flags and be able to start our application with, for example, different persistence layers, like various, like we may want to have an application which supports several databases and, for example, in-memory stub repositories. And the code responsible for that tends to be complicated, very fragile, and to grow quickly, especially when the configuration parameters are intertwined and there are dependencies and mutual exclusions between them. So, dependency injection is a pattern which is based on 4 simple ideas. You describe a problem in terms of products, ingredients, and recipes. You declare your products, ingredients, and recipes, and you do not declare individual actions, and you do not order these actions manually. And in fact, dependency injection as an idea may be applied to many domains, which does not look similar at all. Like a DI framework may govern application startup process, or it may solve some kind of an orchestration problem, like it may govern the whole application lifecycle. It may run workflows, for example. There are many build systems which explicitly describe which explicitly describe the problem in terms of dependency injection. Dependency injection may be used to support operating system lifecycle and lifecycle of a distributed system. And in fact, dependency injection tools are everywhere. So when we talk about program languages and runtimes, we have DI frameworks like Spring, Juice, etc., etc. We have some ad hoc dependency injection mechanisms like implicit resolution, and Scala allows us to build an ad hoc dependency injection mechanism. We have things like systemd in Linux, which in fact is a dynamic dependency injection framework. We have various build tools, and we have some tools which are intended to orchestrate distributed systems like declarative deployment tools, for example, Terraform, or whole orchestrators like Kubernetes. And of course, there are some issues with dependency injection and its implementation. So many implementations are flawed, slow, unreliable, and unsafe. For example, in Spring or Juice, just too many things happen in runtime. And for many domains, there is no ready to use good dependency injection tool, or there is no tool which is good enough to be a game changer. And sometimes looking at the problem, we can't even see that it may be reduced to dependency injection problem, or actually expressed in terms of directed graphs. As a side note, I would like to mention that the reader pattern is not a dependency injection mechanism. Yes, it removes wirings from your business code, though you still need to wire your components somewhere and somehow. And in fact, a reader as a pattern, it's an implementation of a pattern called service locator. So, dependency injection automates wiring, but good dependency injection should promote shift left practice or even enforce it. And there are several ways for that. So let's see what complex problems may and should also be addressed by AI. So there is an approach which sometimes may be hard to implement without good dependency injection mechanism, so-called dual test tactic, which actually proves itself to be a very valuable tool. And the idea behind it is simple. Just run the same tests for your business code twice with real implementation of your integration points and mock implementations. And skip real tests if test dependencies, like, for example, a locally available SQL database, are not met. That sounds simple, but in fact, it's an awesome approach. First of all, it allows you to draft your business logic quickly without being distracted by aspects specific to your integration points, and it enforces a solid design. You have to create better abstractions to accommodate both the dummy implementation and the real implementation. And in general, it makes your code more readable, easier to maintain, and it simplifies onboarding for the new team members. Though some say that testing with dummies is not enough because it does not reveal problems specific to the real integration points. And this is true, and that's why we promote dual tests. And some people say that the benefits are not worth the effort, or that it's just hard to write good dummies, and it's even harder to make your application configurable to wire either good dummies or real implementations. And this is true. But from our experience, the return from good dummies is an order of magnitude higher than the investment, and the complexity of wiring can be solved with a good dependency injection mechanism. As a side note, I would like to say that we prefer to say dummies instead of mocks, because people often think that mocks always stand for automated mocks, though automated mocks break encapsulation, and we should consider them evil and never use automatic mocks. Just when you need to stub something, write manual mock or a dummy. So there is another unexpected subject where DI may be beneficial for us. So there is an old false dichotomy that when we design a product, an application, we have to choose either approach to organizing our code. We should use either microservices or write a monolith. And there are some good things about microservices, of course. So we enforce strict isolation between independent software components. They allow engineers to quickly build independent components, and they allow engineers not to interfere while working on independent projects. But in fact, microservices are evil. They shift the integration problem to the right, and they make it hard. Also, they unnecessarily make make systems distributed, even where it can be avoided. And we know that distributed systems are fundamentally harder to deal with. Also, microservices reduce deployment density, like we have to launch multiple processes, and sometimes it's not convenient. It consumes more resources, like when we run some development environments locally. Multiple times I've seen how developers run a dozen of JVM microservices on a MacBook, and honestly, it's never a good experience. So, on the other hand, the alternative to microservices, the monolith, is bad too. So we know that it's hard to wire monoliths, and it's hard to enforce isolation in monolithic applications. Though monoliths have a couple of good aspects. They give us coherence. We always have coherent code base which represents all our work. And we may build all product components together and have good guarantees for their compatibility provided by our typer. And when you make a change working with monolith, and when your build finishes, you're fine. You don't have to modify and test any other repository or component which may be affected by the change. You may always perform global operations with a single command. And you may be sure that there will be no discrepancies between expected and actual code base state. Also, monoliths give us cheap workflows. For example, you may use just one continuous delivery job to build the whole product. We may easily release and deploy our components together. It's a lot easier to refactor the code. And in fact, good dependency injection allows us to get a fusion of both approaches. And we call such fusion role-based applications or configurable monoliths. The idea is simple, again. Just create your application components as independent libraries and write a smart launcher, which would be able to run any specified set of components, reuse their shared dependencies, allow the dependencies to be swapped according to configuration flags. And once you have such a launcher, you may ship all the components as a single application and run all of them together in a single process. And this way, we may have all the possible microservice-oriented flows and at the same time, all the monolith-oriented flows. And we may develop some components in separate repositories if we want, or we may use monorepo and so on and so on. And also, such approach provides us one important and unique property. This way, we may run perfect simulation of whole products on a single machine without any external dependencies, just by reusing dual testing mocks as substitutions for production components. And that may be really beneficial when we collaborate between, for example, a backend team and the frontend team. So, role-based applications, they shift a lot of development problems to the left. And Distage, the dependency injection framework, we're working on. It provides you with features with full compile time safety. And now let's see it in action. A simple example application. So this application will have a repository interface with a dummy implementation and a production implementation. When there will be a service class that uses the repository and an application entry point, the app, that in turn uses the service. So here we are using the functor tagless final, and we have an effect type F with two parameters, where the left parameter is the error type, like there in method up run, there is a throw, and the right parameter is the output type, which in method run is unit. Though don't worry about tagless final. Don't worry about polymorphic code. Distage can wire any monomorphic code if you need it. So once we have our components, we may declare their wirings in juice-like style. So here we declare that there will be an application and the service, and there will be two possible implementations of the repository, the dummy repository and the production repository. This code on the screen is actually enough to launch the application. Note that here we specify an activation. An activation is a list of choices that tells our application which implementations to choose for components which were declared with multiple implementations. So here we declare that we want a repo prod implementation for all repo components. And that means that the application will use prod repository as the implementation of the repository interface. Also, we are using ZIO as our effect type, and we parameterize the definition accordingly. Though if you don't use ZIO, just ignore everything in square brackets, though I still would advise you to have a look at it. Now, let's look at the test code. First of all, we would need an abstract test suite. When we define several different environment traits, each environment overrides the test suite configuration. So in this example, we define dummy env for tests with dummy repositories, and prod env for tests with production repositories. And when we extend our abstract test suite with our environments, and that's it. So to reiterate, it's very easy to switch implementations in Distage. So here we just declare the preferred choices along the repo axis instead of micromanaging individual components. Also note that each Distage test is a lambda, where each argument declares a dependency that Distage will provide for the test. So in this case, the test do something, requests a service parameterized by ZIO, and well, does something with it. So the tests are written in a purely functional way, using your effect monad, in this case, ZIO. And another important tool is memoization. So in this particular example, we declare DB driver shared across all our tests. When I say all, I mean in all the test suites of a module, not just this single test suite. And as you can see, it's very simple to manage. The minimization in this stage is very simple to manage. There are no global variables. There are no JVM shutdown hooks. There are no shady global objects with lazy vals that do side effects when they are used. So no such hacks are required. And here DB driver will finalize immediately after all the test suites finish. So everything, including lifecycle management of the memoized resources, is handled by Distage. So again, memoized components are shared across all the tests. They shut down gracefully. There are no global singletons involved, and different test configurations may have different memoization contexts. So DB driver from production environment will never be reused in dummy environment. Unlike manual memoization provided by Distage is generally sound and correct. And here is a code snippet showing a role definition. A role is just a replacement for a main method. But unlike main methods, there may be several roles in one process running at the same time. So combined together with automatic application composition, roles allow us to easily run multiple components or multiple microservices that compose our product in a single process for simulations or to simplify deployment and increase deployment density. We use the term multi-tenant applications for applications that can run multiple roles. On the bottom half of the slide, there are two examples of running a multi-tenant application from command line. So the first line would run two roles, users and accounts with real prod integration points. And the second line would run them with dummy repositories and dummy transports, which may be very useful for quick simulations, which are crucial for real continuous integration. And the last important concept in this stage is integration check. So integration checks allow you to define a simple precondition check, which would prevent your tests or your application from starting if the check returns false. On the slide, there is a screenshot of IntelliJ test runner, showing a real test suite where dummy tests were executed, but the tests that required an external Postgres database were skipped. In this particular case, they were skipped because we did not launch the Docker daemon, and the test framework couldn't start a Docker container for Postgres. And there is a code example on the screen defining an integration check. And as you can see, it's pretty easy to do. So integration checks were run before all startup actions, providing you very fast feedback and allowing your application to fail as early as possible if an external dependency is missing. Or in case of tests, integration checks allow you to skip those tests that can't be run without an external dependency and run the rest. Also, integration checks help you to implement the dual test tactic. So, as I said before, when you run your business, the tests for your business logic twice. First time against dummy implementations and next time against real implementations. And skipping the tests that can't run without external dependencies, it really simplifies onboarding because a new developer, someone who just starting with the project, does not need to set up all parts of the environment before they can start hacking and testing the code. They can just clone the repo and start immediately. And now this is the time for our demonstration. So I'm going to stop the screen sharing and hand over the steering wheel to Kai.
Hello, my name is Kai, and I'm going to show you a few things Pavel talked about in our live session. So let's assume I'm a new developer joining the project. I'm going to check out the project to start with. And I just checked with the project and I want to get on board. So the first thing I do is run the tests. We run the SB tests and let's see what happens next. All right, so the tests passed in, well, some capacity, except some of them didn't run. They were skipped because the Docker daemon isn't available. So I didn't run the Docker daemon. So let's run it. So we're going to wait for the Rancher desktop, basically for the Docker daemon to start. All right, seems like I'm getting there. All right, let's launch. Let's run the tests again. See what happens now. All right, so now all the tests ran, and the tests that were skipped previously now passed. And that's because Distage has set up the environment for the tests running. This environment, we call it a scene. So using an analogy, a scene is a place prepared by somebody, but either staff, where the actor will then come and perform on. And in this case, the actor is our application and the teaser staff is Distage, the framework. So this is a very precise definition for our use case that we're going to use from now on. So we know that Distage can prepare a scene for our application. And as you can see, the Dockers were set up for us. So create a new container and let's see. Yeah, the Docker is here. And to do this, to run the test, we didn't have to have Docker Compose installed. We didn't have to know anything about Docker Composer, that is a thing that exists. And we just had to launch SBT. So we think this is a good improvement over the regular Am I on? All right. So This is a good improvement over the regular onboarding experience. Many times I've seen developers spend days, hours, weeks onboarding. And in the case of Distage, you can start hacking within minutes of joining a new project. We think this is a qualitative improvement. So now let's continue and actually try to hack the project. Booting up. All right, so all right, so let's look at the application I've got here. So what we have here is an application that allows us to, it's a leaderboard application. It allows us to upload scores for users. It allows us to upload user profiles with their information they want to share about themselves. It allows us to, for users to get information for other users, and allows us to clear the leaderboard state to get the scores and understand who has the biggest score and who's the leader. So let's look at the endpoints we're setting up here. So this is the HTTP server component. It just sets up an HTTPS server. It constructs it from the routes we assemble here. This is a component that provides the routes. So we have, let's check. We have a few of these. We have the letter API here. So this is one of the endpoints that we have. This allows us to clear the letter state and upload user score. So the actual data manipulation here is through the ladder persistence component. So let's check its implementations. We have two implementations of the ladder component. So one of them is using PostgreSQL to manipulate the data in a persistent way, and another is an in-memory dummy implementation. So it's just an immutable hash map stuffed into a mutable functional ref, an atomic reference, basically pure functional atomic reference, whatever. And here we update it. Here update the map stored inside the reference with a new value. All right. So we want to see how this dummy version of our application works. So let's try to launch it. So we're using the U flag shown earlier to set the repo access to dummy and launch the application. All right, so we have an application here. Let's try to find out how to use the API. So, all right, we submit a score. And now let's look at the letter state. So here we have one user with user ID was submitted before with 100 score. We can update the score, and we have a new score here. So it works. But then this is a dummy or an in-memory implementation. So once we rebooted the application, we should probably have nothing here. All right, we have just an empty list. So our application state is not persistent when we're using the dummy repositories. So let's try to run it with persistent storage. So we switch our repo implementation to production implementation, and we switch our scene implementation to managed scene. because we don't want to, because we want Distage to set up this Postgres that we need for us. We don't want to have it already and have it running. All right, so it launched. Let's say I post again. And what is the state of the letter? So actually we have a lot more stuff here than we actually submitted. And that's because this Docker container is the same Docker container which is for running tests. And so we have a bunch of test data here together with the real data, but this is good because we have persistent data. In fact, we can add some more scores, and we can drop it and launch it again, and it will probably still be there. You'll have all the scores from before. So this is real person storage. It doesn't depend on the memory, the state of the application. All right. Now I could try to run it with a non-managed scene, but again, I would have to have Postgres running at the coordinates I expect them to in the configuration. So our port here differs from the randomized port that Distage generated for us. It's to run, but I never know. All right, so this application we have here actually has multiple roles. So we tried the ladder role, but we also have the profile role, which is a separate API for user profiles. Let's try to run just that one. Right, so we have the profile API, and let's insert something and check if we have it there. All right, so we have, all right, yeah, since we have these scores from before, we actually have already have the rank or position in the leaderboard and the score attached to this profile. But because we're just running the profile application, we can't query the ladder. We don't have that endpoint running. So that's what Pavel was talking about before. You may have flexible monoliths in which you may request a set of product components or microservices and run them in the same process. Now, if I were to run all my product components at the same time with dummy repositories, I'll show it to you right now. I'm going to run both ladder and profile at the same time. I would have a perfect simulation that would start instantly, or, well, it would start faster than the other one. And it's another qualitative improvement on the status quo. It gives very important benefits to our colleagues that work in the front end, because they may get their own isolated backend environments running their machines locally, and they don't have to interfere with each other like they would in a remote with shared remote environments. It's going to quicken their feedback loop, so they have to wait for lots of GVM microservices to start in their Macbook. They have to care about Kafkas, relational DBs, setting anything that up, because everything is going to be stored in memory, all dependencies will be mocked, and the only way for applications to change is through the API that the front end uses to communicate with it. Front developers don't even have to have Docker installed in their machines to interact with backend applications, with mocked backend applications. You can just keep developing. And it's probably you would agree that it's painful to watch when a front-end engineer struggles when someone else modifies their work inside a shared remote environment, or when a front-end engineer has to spin up their own isolated remote environment, or set up a full local environment and wait for it to start, if it starts, because it can fail for a lot of incomprehensible reasons. So while this approach mainly just shortens the feedback loop, it isn't just a quantitative improvement in time. In some cases, it may shorten feedback loop so greatly that it could be a qualitative improvement, because Scala applications developed in that way aren't just backend first anymore. They become more accessible for those trying to develop on top of them. So let's look at another interesting part, which is the test for this application. So previously, Pavel talked about the dual test tactic, and I've shown you rules from the command line. So let's look at the code instead now. We have a test here it's abstract in the sense that it doesn't know the concrete implementations of the components it works with. We can actually run it against multiple implementations of them, as Pavel said before, and we don't call new anywhere. Whenever create anything, our tests just receive abstract implementations. And here we receive abstract implementations through our parameters from a Lambda. But here we use ZIO environment to request our parameters kind of implicitly. Right here. So instead of specifying the components manually, we let them be inferred from our usages. So we require a ladder env component or ND env component, and they're just brought by these usages here. So if we delete a chunk of code, the new environment will be inferred that only uses one of those components. So we could add more code here and not have to add any new components to the header like here. This will just inferred. So you may know that ZIO environment is actually a reader monad. I believe there was a slide before talking about reader and the fact that reader is not dependency injection. It only serves as a service locator. It can locate, it can query, get you something that's already there, but it doesn't wire things. And we can prove it by using them both at the same time in non-overlapping ways, non-overlapping use case, because we have ZIO here, we have Distage here wiring the object graph and creating things, and we have the reader monad querying things, just getting them as a substitution for writing function arguments. And these are totally non-overlapping use cases. All right. And let's talk about actually running these tests. Here we have the concrete test classes that inherit from the abstract test suite. We just mix the test suite with the environment traits. And the environment traits, they again don't do anything funny or don't create anything. They just specified that our activation is specified that for all repos, we want the for all components on the repo axis, we want their dummy implementations. And this is exactly the same thing as specifying the repo dummy flag in the command line. We did it before when we used the launcher. So last but not least, while Distage is a runtime dependency injection library, that doesn't mean you have to give up the convenience of having all of your wiring checked at compile time. That's the convenience you have by default when you manually wire your object graph by using new everywhere. So we can actually have type safety, compile time safety, even while we use the runtime dependency injection framework. So this component here is actually going to, so even though it's a test suite, it's going to run at compile time. Actually, it's going to run runtime too, just in case you wanted to, let's say, set a debugging point, or maybe think that there may be some difference between your runtime and compile time environments. So it's going to run twice, just in case, but mainly it's going to run once, and it's going to run when we compile. So let's try to break the application. Here we have our wirings, and where will we specify what goes where, and let's just delete a wiring and try to recompile. All right, we just failed to compile and we didn't try to launch anything. and we have a reason for the error. It says unsaturated access, ladder, repo dummy, which means that along the axis of repositories where we have two choices, we're missing an implementation for ladder along one of those choices, which is a repo dummy, which, I mean, we know it is the case because we have the only time we set up a ladder implementation is a Postgres implementation, and it's tagged as repo prod. And we have nothing here in repo dummy. So Distage tries to check all possible combinations of all possible configuration flags, and sees that if we were to try to use the dummy access, we would fail. And even if we don't use the checker here, we would still, at runtime, we would still fail way before we try to launch anything or do any kind of side effect, because we would first try to assemble the object graph and see that we're missing a component before we executed any effects. And because of that, because we, unlike, for example, Juice, that does everything at just in time, doesn't actually know the shape of the graph ahead of time ever. We know the shape of graph ahead of time, and we can compute it actual at compile time without executing any code and check that it's well formed, that all variations of it are well formed. So that's it for a quick demo. And now would be the time to ask your questions if you have any. So please ask your questions, and please tell us if you need any additional clarifications. I see there are already 3 text Q&A questions, so I'll just hand the mic over to Pavel to answer them. Thank
you. Yeah, so I hope you can hear me now.
Yeah, perfect.
Okay, I'll just give me 1 second, and I'll answer all the questions.
So the first question is, can we use Distage with Java? And the answer is no, because it's fully dependent on Scala. It's written in Scala for Scala, and it uses Scala macros as is, so there's no way at all.
So can we use Distage with Java? Yes and no. So it would be enormously inconvenient to use Distage from Java. Though you can, of course, use it in Scala projects to wire your Java code. That's not a problem. Though, of course, if you don't use Scala in your project, no, Distage won't work for you. Are there any production products that use Distage? Actually, yes, plenty of them. I think that at the moment it's being used in several banks. I think that there is a team at Oracle which uses it. I think that, from what I know, about half of text traffic in the United States is managed by a product which is built on top of Distage. Yeah, so yes, there are multiple production
means
usages.
SMS messages.
Yes, I mean short texts.
What about Scala 3 support? Actually, we're working on that right at the moment. So yeah,
yes,
it's going to come soon.
So currently, you may test our preliminary Scala 3 support by switching to our snapshot version. It's not perfect yet. There are still some bugs, though most likely you won't encounter them if you don't use path-dependent types. So I won't advise to try to use Distage in a Scala 3 environment for now, though you may already try to test it. Any other questions?
Yeah, so we've got another one that says, it seems Distage is mostly intended to be used with TF style. If we use ZIO2 ecosystem with its built-in DI, does it make sense to switch to Distage?
Yeah, so first of all, it's you don't have to use Douglas final if you use Distage. As I said before, it can via any flavor of Scala code. Now, regarding ZIO2, currently we do not provide implementations for TF helpers for ZIO2. It's gonna be fixed in foreseeable future. And though you still may use Distage with ZIO2. And now regarding the embedded dependency injection mechanism in ZIO2, in fact, it's not true dependency injection. It's still service locator. It's still ZLayer. It's just become fancier. And in fact, the fun fact is ZLayer is based on our code. There is a small library named izumi-reflect, which ZLayer is built on top of, and we are the authors of that library. So I actually know what I'm talking about. ZLayer is not a bad tool. And in ZIO2, it has, well, more sugar. Though it can't do all the things Distage can easily do for you. It can't actually help you to have to apply role-based approach, and it won't help you with dual tests. So if you write something simple, I would advise you to stick. I mean, really simple, small projects with just I don't know, several hundreds of lines of code. I would advise you to stick to ZLayer if you're used to it. Otherwise, I would advise you to consider using Distage either with ZLayer, together with ZLayer, because they may play nicely together, or just Distage. Yeah, so this is my opinion.
Perfect.
And essentially, John himself, I think there are, on several occasions, he essentially said the same. Like, if you have a simple project, ZLayer would be a perfect choice. Otherwise, consider using Distage. Yeah.
Let me answer this question again, a bit shorter. So does it make sense? I think it does make sense because, I mean, using ZIO together with Distage in a monomorphic way, we actually have special support for that. I mean, you've seen in the live coding session that tests support ZIO environment to use them. And we also have special support in the wiring to use the ZIO.
This particular question, it was about ZIO2, and we don't have support specifically for ZIO2 yet.
Yeah, but it's basically the same thing. It just needs an update. So we have the
support
for ZIO1.
We'll deliver it eventually.
We have the support for ZIO1, and we'll have the support for ZIO2 once we have. I mean, there's been a lot of updates like SFX3, Scala 3, ZIO2. So they need some time to all be finished. But basically, it does make sense. It did make sense before in ZIO1. It does make sense right now. And we have special support for that specifically as well.
Perfect.
Well, there is...
Oh, go on, carry on, Pavel.
Oh, yeah. So there is another question regarding performance metrics or goals.
Yes.
I may say that Distage is, well, it's very fast. Injector is cheap. And unlike with other runtime dependency injection frameworks, in general, you shouldn't worry about the price of its invocation. Yeah, so essentially that's it. Distage is fast. It still does some job at runtime, though most of the job is done during compile time, and you may expect sub-millisecond times for injector invocations.
Okay, let me answer this question again a bit shorter. Well, for Juice, for example, the main problem with its performance is that there's a lot of reflection at runtime, and the way JVM does implement that is pretty slow. So in case of Distage, a lot of reflection is done at compile time. So at runtime, we're basically doing a lot of hash map operations, and we have optimized those. So it's fast. For example, we have a project with about 2,000 components and a test, well, again, a compile time test that checks that. And well, most of the time spent on test is class loading, and the injector itself finishes in about 3 milliseconds. So it's basically cheap enough to use it locally per request and some such, and not have to worry about it.
Yeah, and so essentially we do not do any kind of Java reflection in this stage, I mean, at all. And it works anywhere. It may work on Graal VM, it may work on Scala.js. We never tested it, but
Wait, no.
From working on Scala native.
Scala.js, we have a build for Scala.js, and we have a build for Graal native. We don't have Scala native, but we have, so the Distage example itself, it has instructions to build for Graal native, and we have Scala.js implementations for a few years. So yeah, you can use it in Scala.js, you can use it in Graal native, so it doesn't depend Java reflection at all.
Can we hotwire components while the application is running? No, it's not a dynamic dependency injection framework like for example, well, systemd. Though there is a remedy for that. Essentially, you may reuse a context, a set of instances built by one injector. You may reuse these instances in another local injector. So you cannot rewire a graph, though you may create new graphs which reuse parts of the primary application graph. And essentially, this approach is a lot easier to reason about. So like in OSGI, which is a dynamic dependency injection framework, and in systemd, which is a dynamic dependency injection mechanism, they are, yes, of course, they are more powerful, though it's maybe hard to reason about what's happening during runtime rewirings. And in our case, everything is immutable, and instead of rewiring, instead of taking care or complicated three-phase lifecycle like create, update, and clean up, instead of taking care of such complicated life cycles, you may just reuse pre-built components and create new local injectors. So that's the idea. You can, so to be short, you cannot dynamically rewire your application. You cannot change the content of the injector, though you may reuse that content to build another set of instances and components. And we think that it's in general, it's more productive when dynamic dependency injection, which is fundamentally harder to reason about.
Like, yeah, basically. So if you want, you can create new components, but they would have to be in nested injectors. So you can create new stuff, but you can modify old stuff. But then you can also use any technique, to turn immutable values into mutable. For example, you can store your object graph in a mutable reference and update it if you want to. Like, I mean, that would be crazy, but it's possible. But then it's not really supported.
Any other questions? Anyone?
I think that may be it, guys.
Cool.
Cool. So look, thank you for everyone for coming, and thank you for the great talk and demonstration, guys. It's been really educational. So just to wrap up, we will be having a pause over Christmas and the early part of January, but we will be back on the 30th of the 1st with Marcin Krakowski, who you guys might know from doing other meetups and also functional Scala as well. He'll be doing a live demonstration with the type level stack. So we hope to see you all there. Please do feel free to check out the YouTube video. We'll make sure that gets sent around if you want any points of reference. But thanks very much for coming.
So thank you everyone. And well, see you next time. Bye.
See you next time.